Okay, thank you, Emil, for the introduction. Thank you, Emil, for this introduction. The title of my talk is Energy Conservation and Emission Reduction in Wireless Networks. And it will cover some different blocks here. First, I will give a short introduction to ICT and sustainability in general. Then I will talk a bit about RAN energy efficiency basics, I have called that block, which is about what has been done in this area the recent years. I've been active for 10 to 12 years in this area, a much what we are focusing in order to save energy in wireless networks. Then I have a block that goes into the RAN energy efficiency trends directions right now. I also then have a block that is a fairly new area I would like to introduce here that I call low carbon RAN. And finally, concluding remarks, or rather a summary of the talk. But first, let's have a look at this vision, I think, that we set up for, well, some years ago when we were starting thinking about 5G. And I think now in 2022, we are probably have much of this are happening. We can see down to the right, we have a factory, smart factory, and that is actually happening now. We're deploying 5G and private networks and so on there. We see a remote surgery down to the left there that is maybe not happening yet, but it's well on the way. We see a smart city up there. We see connected drones, drone delivery, and so on. Actually, this winter, I think I heard that in Sweden, in Stockholm, for the first time, a defibrillator had been delivered by a drone out in the Stockholm archipelago, I think. So instead of sending ambulance or ambulance helicopter, it was possible to send out a drone with that equipment. So much of this is happening. And many of these solutions are, of course, also good for sustainability perspective. You might have heard about something called the enablement effect, which then actually is about how these ICT solutions can contribute to save energy or save emissions in other sectors. Over the years, there have been a lot of studies around this. I think one of the recent ones is from 2020, when the GSMA published a report, the enablement effect, where they looked into some of these technologies, for example, smart buildings, where they looked into using smart meters and building management and to improve the energy efficiency and also affect people's behavior to save energy in buildings. Smart energy, where they again, also you might have heard about smart grid, where meters are used, and also then intelligent solutions to match supply and demand in the networks to get a better fit for the energy use and supply. Also allow then small scale renewable energy producers to provide energy there. Smart living, smart health can also be smart working that we've done a lot during the pandemic, for example. Smart transport and smart cities, that is about, well, it can be fleet management, route optimization, and also apps and so on that you use to facilitate charging of electrical vehicles and so on. Smart agriculture, that was actually an area where they didn't see so much enablement potential yet, but there is believed to be in the future. And smart manufacturing can be storage and inventory management and so on, that allows you then to adjust your energy consumption in terms of, say, lighting and cooling and so on in this. And what was concluded there was that overall then that mobile technologies actually contribute 10 times to society in emission reductions. And that is then compared to the emission that mobile technologies cause, they can actually save 10 times of those emissions in other sectors then. Similar study, as I said, has been done before. The one to the right there summarize a quite famous report called the Smarter 2030 report, done by the Global Sustainability Initiative, GESI, from 2015, that looked at the entire ICT. They also come to a similar conclusion there. And of course, there are also things can be debated about this. I mean, we can have this rebound effect that when you start use this technology, actually that increase the use and so on. So there are, of course, things that can be questioned here, but I think we see a clear sign that the ICT technology definitely have a role to play when it comes to implement sustainability in other sectors. But just because of that, I guess we should not forget sustainability itself, of sustainability of ICT itself, and in particular then the wireless networks that actually are out there to provide access to all these services, and that is what I mainly will focus its presentation of, as you might have realized. So looking then at that, where is energy consumed in that case? And here I have drawn up a typical network operator, and there actually around 85% of the energy is consumed by the network. The remaining part then is consumed, say, in the offices, transportation. I mean, it can be business travel, it can be maintenance travel out to sites and so on. And then looking at the network, then you see you have the mobile network. There is a transmission there, fixed network, some operator-specific data centers. Then, of that, around half of the network consumption actually is consumed by the mobile network, and in the mobile network, 75% of the energy is consumed by the RAN sites. So obviously, it's important to focus on the RAN energy efficiency. I should also say then that in this picture, as I said, I focus on a typical operator here. So here actually content providers and also like these big data centers, Facebook, Google, and so on, they are not part of this. I have focused on a network operator here. So that brings us then to RAN energy efficiency, and the first real block of this presentation, then the RAN energy efficiency basics. First, I would like to introduce some nomenclature being used in this area and in this presentation, so that you will know what I will be talking about. What we see here is, well, maybe not the complete network, but it is typical RAN sites in terms then of energy consumers and how it is consumed. So to the left there you see the power, or then if you integrate over time, the energy comes in, PAC. And then you have rectifiers then converting to DC. You might have some power backup in terms of batteries and so on. You have air conditioning, lights, etc. And this we then call the site infrastructure. And typically when we talk about site energy efficiency, this is what is meant, and that actually the DC power you supply to the base station divided by the AC power that you get into the site, so to say. So it's more or less the inverse of the PUE, the power usage efficiency that you might have heard about in data centers and so on. Then we have the base station, where you have the baseband, the radio units, and so on, and then output power then that produce output power in the air. And sometimes you hear about base station energy efficiency, and that is typically then the sum of these output powers divided by the input power to the base station. And then, of course, over the air, you transmit this to the user terminal, where you get some sort of useful output. I call it a service performance indicator here, and it can be data volume, a coverage area, In terms of MTC, it can be the number of users, number of connections. Your LLC, there are actually metrics defined based on latency and can also be user performance and so on. But those are the three parts then, and quite often when we talk about raw energy efficiency, this is the part that we mean actually the base station combined with the air interface then. So more or less the useful output divided by the input into the base station then. So I think quite well known is data volume divided by the input power then in terms of bit per joule or gigabytes per kilowatt hour, for example, or measures then on that. Having that said, I also want to emphasize then that it's also important actually to focus on the site, because that is also an important part of the network when it comes to improving it. So going on then, what challenges do we have here and what energy saving potential? Well, below there you see kind of a graph. As you might imagine, the traffic experienced in the network varies quite a lot. The blue curve there shows actually, I think it's 2 days traffic, illustrative there, how it goes up and down depending on hour of the day. And then one could expect, well, that also the energy consumption of the equipment probably would scale similarly. But in fact, when you look at this, it doesn't really do that. It's rather the yellow curve. You see there is some variation, but not so much. And why is that? Well, there are some reasons for this. First thing is, in a wireless network, that's an access network. That means that the energy is not only there or is not only consumed when you deliver data. A lot of energy is also spent on providing coverage so that you actually have the network built out there and you are able to access it when you need. So it's two purposes why you have the network there. And that means that many base stations are actually out there without load or very little load. And looking on the network level, then the load is actually fairly low. You see an example there in the middle. It's from a European city. It's 600 cells. Average utilization, and you see it goes from around 2% up to 14%, which of course means there are cells there that are highly loaded. But when you look at the whole network average, maybe around 10% on the average. And then we have the typical behavior of this type of equipment. That's I try to illustrate to the right. There is actually a rather large static power consumption there, say around 40-50% of the full load power consumption then. And considering we are moving around these 10% load, and you see you're moving just along a short line of that, which then means that you actually end up with this yellow curve. But of course, there might be ways to do here so that you can more approaching the green curve. And that is then what I will come into on the next slide, how to harvest the energy saving potential that we saw there. First thing is, of course, what I call resource on demand scaling. As you know, in a wireless network, you have a lot of radio resources that you offer then to carry traffic. And naturally, you would like this to only provide as much resources that are needed, but you also saw the traffic variations. You actually need to have quite a lot of resources out there, but then you should be able to scale down these when they are not needed. That's the first thing, but that's not enough, because in case, I mean, you scale down these resources, if the power consumption doesn't also scale with the resources, then of course there's no meaning with that. So you would like to have this sort of variation, and you would like to push it down towards the green curve there. And that is continuously being worked on, being improved. Quite a lot has happened during the years I have been here, but we are also working quite a lot with what I have called shutdown capabilities here. And that is actually when you're down here that you are able then to deactivate components of the base station, which then in another way brings you down towards this ideal curve. That is actually a very important way of saving energy. So what does that mean then when I say shutdown capabilities? Well, it's about and connect this to the radio resources you use. First, to the left, you see I mentioned the time domain, and that relates to shut down hardware components in unutilized time resources then like symbols or time slots or even more. If you talk about symbols, which I illustrate here, then you would need a fast reactivation, which means a limited amount of hardware can be shut down. In the example here, you see what I call symbol shutdown. Sometimes you might have heard about DTX, discontinuous transmission, that's the same thing here. So you have a base station that is idle, but it still need to transmit some mandatory signals, the reference signals here that comes every fourth or every third symbol here. But in between, you can actually do a sort of micro sleep, which means that you deactivate parts of your power amplifier in there. And that is actually something that is very useful in saving energy on a network level. Next thing is the space domain. We have now definitely from LTE and onwards, we have MIMO in our systems. With 5G, we also have the massive MIMO, which then means that you have a lot of RF channels and a lot of antenna elements, which probably not always are needed. So the idea here is that you shut down RF channels when the conditions allow. There you typically then try to shut down more than just parts of the PA, probably more of these RF channels. So it will be a more semi-fast reactivation here. An important thing is also then that when you shut down RF channels, you actually take away some of the output power. So there might be necessary to do a sort of coverage compensation here. And this could be an example, as I mentioned, RF channel shutdown, MIMO muting, you might also have heard about. That's examples of this type of shutdown capabilities. Then when we mentioned the frequency domain, an example here is then that you shut down the entire carrier when the conditions allow. And that is typically used for capacity carriers in low traffic. For example, during nighttime, there might be much lower traffic than during the busy hours, and then you don't want to need all the carriers or cells that you have out there, and then you can shut them down. Typically, this works on a more slow time scale. You can shut down a larger amount of the hardware and so on, which also means the activation can be very slow. Sometimes I get the question, so which one of these are most important? And I would say you shouldn't put them against each other. They are rather complementing. As I said, the time domain here, especially this symbol shutdown, is very useful because that works always. I mean, even when you have high load, you might have empty symbols on the radio interface, and then it's good to be able to deactivate the PA there and save some energy. And a very good thing there is that this actually acts after the scheduling decision. So you can detect, okay, there is an empty symbol, then we sleep. The other two, there you actually take away resources from the scheduler, which means that if the traffic goes up, then you might actually have a hit on the performance indicators because not all the resources are available to the schedulers because you're waiting for the hardware to activate, so to say. So that's a slight of difference there, but they are then, on the other hand, saving more energy when they are in use, so to say. So from that side, they complement each other and focus a bit on different situations. Related to this, I would also then like to say some words about design philosophy here. I call it the energy saving cube. Connected to these shutdown capabilities, there are 3 dimensions there. I call them breadth, duration and depth. Breadth relates to extending the energy saving then or shutdown capabilities to more scenarios or more resources. For example, for the carry shutdown, it can be that in addition to the nighttime, you might be able to identify also other times when you can use it. Duration relates to extended the time an energy saving action can be active. Depth relates then to extending the amount of hardware that is deactivated. So, and then of course there are connections here between them. For example, if you increase the duration, then it's quite intuitively to see that then you can also deactivate more components. You can then have a deeper depth in your sleep, so to say. But an improvement in each dimension results in increased overall energy saving here. And I have two examples here. Actually, they are on how to increase the shutdown duration. First here is what I call power saving scheduling. So consider a situation then to the left there where data to use are scheduled in every TTI. That means that no time domain shutdown is possible. Well, there might be some symbol in there that you might shut down, but no larger chunk of time to shut down. If the scheduler instead would allocate the data as in the right figure, pack the data in time domain, then you would all of a sudden actually be able to do shutdown in TTIs 1, 2, and 3. So just by doing that, you actually free up quite a lot of resources where you can do shutdown then. This may, of course, affect the delay and latency, so you need to keep track of your data there that you're able to do this so that you don't affect the performance in the network. But that is one simple example then on how you can increase the shutdown duration. Another one that is quite well known is the protocol design of 5G NR when that was made 5-6 years ago now. Starting point then was the 4G LTE, where we have a 10 millisecond frame. If we have an idle 4G LTE air interface, then you actually have every 0.2 millisecond common reference signal being transmitted. They are actually so often there, so I haven't drawn them in this figure. But you have something quite abound on all over this, but you just have this very short few symbols where you can sleep, but not more. And you have the synchronization signals twice per frame, the red ones, and the broadcast channel then once per frame, the green ones up there. Then in 5G, also there is a 10 millisecond frame. One important thing, there are no common reference signals there anymore. All reference signals are dedicated, so they are not there until there is a user there. Synchronization signals and broadcast channel are transmitted more, so to say, block-wise in different patterns, so-called SSB sets. And these sets are fitted within a half frame, as illustrated there, which then is 5 milliseconds. But the periodicity of these sets can be configured then to everything from 5 up to even 160 milliseconds. The default is 20 milliseconds, which I use in the simple calculation here below. So what we then see is that in 4G LTE, you had this sleep duration of 0.2 millisecond between the common reference signals, while in the 5G NR then it's actually 15 to 20 milliseconds between the SSB sets that you have here. So it's actually 100 times longer sleep duration that this protocol design enabled then. So that is something that actually then improved the energy saving possibilities compared to LTE by 5G. So that was a bit about typical basic ways of saving energy in wireless networks. Now I will move on then a bit going into the trends and directions that are much worked on today. First thing is what I call here multi-antenna RF or transmission efficiency. And this goes back to in recent years or more or less with 5G we have seen, but also with the other technologies, that the total transmit power of base station has increased. And this is because we have the wider bandwidths, more carriers, more antennas, and so on. And this naturally need more power, but it also contradicts the energy saving objectives, because you have more powerful hardware typically consumes more energy. In line with that, then there is what I would say new energy saving track now, and that is about improving the energy transmission efficiency. In this example, then by having a more ultra large antenna array, see it here, so many antenna elements. So the simple idea is simple, have that as a way of getting more antenna gain. So actually you get you can maintain the coverage or maintain the output power then by getting less power from the power amplifier, so to say, and utilizing the antenna instead to amplify this up. And we have seen some tests here that actually are able to save about 30% power by utilizing such designs then in Massive MIMO. Now I comes into the site area that I mentioned before when I introduced the nomenclature, and one trend is also to simplifying sites. This has been there for a while, but I think it has come even more recently. Traditional DRON sites with air conditioned equipment rooms are not so energy efficient, only around 60% site energy efficiency there. One trend then that you have been there for some years now is the CRON deployment, where you centralize your baseband. So you have one site where you have like a baseband hotel instead, and then you have only remote radio sites. And these remote sites can then be simplified and typically free air cooled. So it's only in the central location you need air conditioning. And this can actually improve the site, overall site energy efficiency quite a lot. These solutions are also now coming more and more for the single sites, so to say. Instead of having equipment rooms, you have one cabinet where you put everything. And you can also have a more simplified than that. You just have a pole deployment. You might have heard about blade sites and so on, which then also improve the site energy efficiency significantly. Over 90% efficiency are typically possible now in these solutions. Another site related area is actually to now start to actually monitor and control site equipment in a much better way than before. Traditionally, there has been a rather poor coordination between the active equipment and the more passive things like the power supply, power storage, and so on. Now this is more tightly coordinated, linked together, and jointly managed. So you can coordinate much better, which allows you to save both energy and cost. For example, if you know that now I will have a rather high load on the base station equipment, then you can then ramp up the power supply and the cooling, and when it goes, you know it will go down, you can then adjust down this instead of having them running fully all the time, for example. And there are also many other things that you can do with this area that typically then improves the energy efficiency of the entire site quite a lot. Another thing, AI, of course, intelligence for energy saving, that has been there for some years, but it's very high on the agenda now. Already today, there are solutions out there. Typically, I would say they are there now to support and increase utilization of the energy saving features we have. Few examples are there in this slide. We have co-coverage detection, where you actually run AI on the a whole bunch of measurements reports. So you can identify the candidate cells for energy saving measures. You can actually do this both intra-site and also inter-site. So you actually can then easily know which sites and bands that actually have the same coverage. So then you know that now I want to do shut down these cells or these carriers, then I can do this because I know this one I keep and it has the same coverage, so I can do handover of the users there, which then makes increase the use of this and increase the energy saving then. Traffic forecasting, of course, in a quite detailed way using spatial temporal data. You can even use weather forecasts, forecast on how car and humans flow, traffic and so on, to service characteristics. So by taking all these into the AI machinery here, you can get a quite good spatial temporal prediction of the traffic, which then also helps you optimize how you let cells sleep and when you need to wake them up and so on. Another important thing is what I have called parameter optimization here, and that is related to the network management of energy saving features. Each feature have a bunch of parameters that you need to configure, and normally this is done like you have a network area, you roll out this and you set the parameters according to some sort of default. But we know that the traffic and also conditions actually vary quite a lot from site to site. So actually one site, one strategy is better than having the same strategy over the entire network. But with the AI, then you can actually simplify this. You can have an individual parameter optimization per site cell then based on this, and this then maximize energy saving while you keep the KPI stable. In this case, you see how this optimization then have found some more hours where you actually can have these energy saving features active. And AI is then moving more and more and actually also into the RAN. And here is an example of a study. Actually, it's a master thesis we did together with a student from KTH on radio resource adaptation then based on reinforcement learning. So here we actually adapt the massive MIMO channel configuration, the bandwidth, and what we call spatial multiplexing factor, then the number of scheduled users are jointly optimized with this reinforcement learning. And as a baseline, we have a quite advanced system already there with time domain energy saving features then acting on different time scales then. But with this reinforcement learning based resource optimization, we're actually able to save another 15% on top of this fairly advanced thing. There is a conference paper that you may look into if you want to know more about this. But this is actually just one example how this can then come into the RAN network as well on the resource configurations. So having that said, I come into the last real block of the talk, which I then call low carbon RAN. And the background is, of course, the climate change and climate action that has become a global priority. I think no one could have missed this with the UN Sustainable Development Goals and also the Paris Climate Agreement, which then, where more or less all the countries all over the world have a promise then to take positive action to limit their emissions, both to reach carbon neutrality, but also then net zero finally. And there are then different promises being put out here. And that, of course, also it has been a strategic goal for the mobile network operators. There are examples here to the left. You see some regulator actions here in Germany. For example, there is a requirement to assess the carbon footprint of the digital infrastructure. In France, there are actually they will actually use the operator carbon reduction as a basis for spectrum distribution and so on. In ITU has developed a sort of pathway how much energy or how much the emissions need to be reduced in order to follow the Paris Agreement. This is done for the ICT sector. And also GSMA have activities in the area. Operators have set up target when they will, how fast they will reduce their carbon emissions, and also how fast they will deploy green energy and so on. So a lot of things is happening here. The tool you typically use then when you want to assess your carbon footprint, that is then life cycle assessment. I'm not an expert on this, but I know there are experts both in KTH and also RISE and other organizations here that probably knows this better than me. But what you do is that you actually look at the whole life cycle of a product, from the raw material selection and acquisition to production, transportation of the product from the factories to the place where they are deployed, then of course the use, and finally end of life treatment then when you take them out of service and you try to recycle and so on. As I said, many studies have been done on this. This just shows some illustrative pictures from OA sustainability report of how it typically can look for different types of equipment. You see mobile devices at the bottom. There you see that the raw material selection and acquisition and the production is responsible for a very large part, and that is both because the energy consumption is very low of such a device, but also because we typically don't keep them so long. We just keep them for 2-3 years or so, then we want to have a new iPhone and so on, and that of course makes a lot of embodied emissions there. And then if you compare them to the network equipment on the top here, we see that the majority of the emissions actually come from the use phase, and that is the electricity consumption there and so on. And that is because one thing, they as I said, that they are fairly energy consuming, but also because they are kept in use for longer time, up to 10 years, maybe longer in some cases then. So which means that you can that embodied emissions doesn't take such large share of this. Yes, that, I mean, that can also be good, because that means you can, I shouldn't say easily, but one way then to reduce the emissions is of course to use green energy. Then you can affect quite a lot of this footprint. But still, embodied emissions is a very important focus area for the mobile network operators and also the vendors, of course. And there is quite a lot of work being invested in this, all the way then from the material acquisition and selection, to use as much as possible environmental friendly there, renewable, recycle, biomaterial, and so on. In the design, you want to make it as lightweight as possible, always looking for new architectures and so on. You optimize the package and transporting in order to keep the weight and the dimensions as small as possible. In the operation, of course, the energy saving actions are important, and also you can try to use as much green energy as possible, but it's also about how you can try to prolong the service life when it comes to the embodied emissions. Then modular design should be easy to repair, design for durability, and so on. And finally, then of course, in the recycling states, it should be easy to disassemble so that you simplify the recycling and reuse of the materials that you have used there. That is a very important work that is ongoing, but one can also ask then, I'm not an expert on this, I'm rather a communication system researcher and designer. So I also ask myself, what can we done in that area in order to reduce the embodied emissions? Of course, we work with the energy saving and the use phase emissions, but there can be things we can do also in the embodied emissions. And one thing is, of course, the deployment and architecture, network deployment, and actually these site constructions may add embodied emissions. I just took an example of an LCA study here that has shown that for a site deploying with a large tower, the embodied emissions actually are similar to the emissions from the use phase, because then the construction of the tower and I think in this case there was also construction of a road to the tower adds a significant amount of embodied energy to the network. So then simplified sites, as I talked about before, not only improve the site energy efficiency, they also allow lighter constructions with less embodied energy. But there are probably a lot of things that could be looked into here, alternative network deployments and architectures from this low carbon perspective. And I mean, now we talk about cell-free architecture, intelligent reflecting surfaces. What impact may they have on this, for example? Probably they are promising here, but it should probably be studied more. We have these antennas where you, I mean, it's just a tape stripe, for example. That could probably be an interesting thing when it comes to reduced embodied energy and so on. So many things to look into. Sharing is an efficient means for the mobile network operators to reduce their carbon footprint. Different scenarios exist. It's quite intuitively that if you look at left there, where we have the traditional way of each operator have its own RAN, that it's probably contain a lot of embodied emissions. First step is then to go to the passive site sharing, where you more or less then gather your equipment. You have it on the same site, but each operator still have its own equipment. But just by getting rid of a lot of towers and these equipment rooms, probably saves a lot of the embodied emissions then for the operator. Next step is then the active sharing solutions, multi-operator RAN, and then the most advanced actually multi-operator core network there, where you actually share all the active equipment and also the radio carrier is shared in that case. So these are probably important means for an operator to reduce its carbon emissions. Other areas could be the operation and management, something I called linked energy to the left here that relates to manage the renewable energy sources an operator might have on the site versus the grid versus the backup. So it's typically targeting a scenario where you have the grid mix is quite mixed. You might have quite some brown energy in there and also some green that may vary over the day. So can you then use your own generation to charge your batteries and then use that when the grid mix is more brown, for example. But you can also do this towards the smart grid that the operator typically then get information from the smart grid when is the supply more green, so then I use it then and try to shift workloads there. This is maybe not so useful in a radio access network where the loads are changing quite rapidly, maybe more suited for data center type of services and so on, where you probably can do a more slow shifting of workloads and so on. But it's interesting areas to look into. The operator can also support other sectors, can use its site resources to offset emissions. For example, if you have these local renewable sources, it can be, as I mentioned, made available to grid, that you can feed when you have possibility to feed out renewable energy on the grid. Part of that can be to implement sort of this demand response models so that you locally then can shave power peaks and so on, and use that to also maximize the use of green energy. When you have waste heat, that can be made available for warming nearby buildings and so on. And then I actually put up an open card here. What else? I say more research is needed in this area. So there are many things that can be looked into here. By that, I actually are coming to the concluding remarks, or as I just called it, a summary of the speech. So what have I been talking about today? First, I touched a bit about ICT for sustainability, where we saw that mobile technologies at least have the potential to contribute quite a lot to society in emission reductions. But then it's still important very important to focus on the energy efficiency of ICT, in particular wireless networks themselves. The coverage, the traffic variations, and the dimension of the peak is a challenge here. Traditionally, we worked a lot with the resource scaling, shutdown capabilities for implementing energy saving then, and this is continuously being improved and expanded to more scenarios. Some trends right now when it comes to raw energy efficiency, the improved transmission efficiency I mentioned, site simplification and this linked energy, and then of course also the AI and machine learning then for network intelligence. And low carbon RAN then that I just talked about, the new area where how can our deployments, architectures, and also operational and management solutions be designed and in order to have as low embodied energy as possible as a sort of complement to this full life cycle low carbon design that is always being worked on. That's it, I think. Yes, thank you.